Okay, so for this last section of chapter 1.7, we'll be discussing linear inequalities in one variable. And an inequality, well, first off, the inequality symbols we'll be using are these four. Mainly we'll be focusing on, I said these four, there are five. We'll mainly be focusing on these four. This one, the not equal to, is technically an inequality symbol because it's not equality, but it doesn't really give us too much information. These four are a little more specific because they're a comparison. This is bigger than that, or this is smaller than that, or vice versa. So, of course, this would be the less than symbol. This is the greater than symbol. And the other ones with the lines under are the same ones as the ones I've just labeled, only or equal to. So this one will be less than or equal to, whereas this one here will be greater than or equal to. So notice when I'm writing LT, it's just shorthand for less than. When I write GT, it's shorthand for greater than. Okay. The ones that do not have an equal to symbol, I will call strict inequalities. So sometimes I'll say strictly less than, strictly greater than, meaning not or equal to. The or equal to ones, the phrasing I'm going to use here is a little unclear right now, but we'll see why it's the case in a second. Well, I guess after these examples anyways. But these are called closed. I'm going to call them closed anyways, inequalities. Okay, now here's what I say about solving linear inequalities in one variable. Solve as you would a linear equation, except reverse the symbol when multiplying or dividing by a negative. What I mean by reverse is that any less thans become greater thans, or greater than or equal to becomes less than or equal to. So just flip the symbol basically. Okay, so now let's take a look at these next examples here. The first example, so think of again 3x minus 5 is equal to 2. How would you solve that? You would add 5 to the other side. You would get 3x is equal to 7. Here we get less than, so the symbol doesn't change. It only changes when you divide by a negative or multiply by a negative, in fact. Dividing by 3 now gives us what? Gives us x on the left, and I guess on the right is just 7/3. So x is less than 7/3 is our solution. Okay. For this next example, it's going to be fairly similar, only since there's a fraction, we can get rid of fractions by multiplying each side by 5 first. On the left, they cancel out, so we just get 2 minus x is greater than or equal to 15. Okay. Now notice the symbol didn't change because we didn't multiply by a negative, we only multiplied by a positive 5. If you multiply by negative 5, the symbol changes, but we didn't. Then subtract 2. So we get negative x is greater than or equal to 13. But now we want to get rid of the negative in front of x. Remember, negative in front is negative 1 times in front. So we can divide both sides by negative 1. And what do you notice happens? That's right. Dividing by a negative reverses the inequality symbol to now from greater than or equal to now less than or equal to. We have x by itself on the left, and now this is negative 13 on the right. And that's our solution. I am a little weirded out by saying these are our solutions because they're not technically proper ways of describing the solution set. And I say that because these right here are expressions that represent infinitely many numbers. So just real quickly, if we were to plot all of these numbers on the real number line, think of 7/3 as being right here. What I want to do is I want to shade all numbers that satisfy this equation, and there's a bunch of them. Like I said, there's infinitely many, and they're all less than 7/3. So they're all going to be to the left of 7/3 on the number line. And I can use an open circle to signify that we don't touch 7/3, or else it would be or equal to. But instead I'm going to use an open parenthesis, and we'll see more of that in the next set of examples. But for right now, I'm going to say this is the graph of my solution for the first example. For the second example, if I want to graph this, x is less than or equal to negative 13, well, the number in interest here, just like there was 7/3, this is negative 13, and it's still less than, it's less than, so we shade to the left. All numbers less than a number are on the left of that number on the number line. But since this is a or equal to, we'll use a bracket instead of parentheses. So the parentheses means we don't touch that number. The bracket means you do touch that number. And right now we're going to see a few examples that go over some different notation on this, and we'll see that right now. Okay, so there are three main types of notation when it comes to inequalities, and they are set builders notation, graphing, and then finally interval notation. I started this because this is what we're going to aim for. This is like the most useful of the notations. It's shorthand notation. It's really nice, but it's something to get used to. So I want us to eventually get to the point where we can just write our answer in interval notation right away without jumping through these. But for right now, I have to explain these. So set builder notation is fairly straightforward. It's kind of like what we got for the previous examples, only we have, well, these decorations. We have the braces and an X in front of this bar. What this means is this is the set of all X values such that X is bigger than A. So here this describes an element. I'm going to write ELT for element. The bar is such that, and then to the right of the bar is the description of where the element lives, basically. So here it's bigger than a number, bigger than or equal to a number, less than a number, less than or equal to a number, in between two numbers, not equal to either of them, in between two equal to the smaller one, in between two equal to the bigger one, and in between two possibly equal to either of them. Okay, so now how do we graph these? Well, I'm going to shade in red where these things live. So here X is bigger than A. Here X is bigger than or equal to A. And remember how we did it in the previous examples. When it was equal to, we wrote a bracket. Closed bracket means or equal to, and an open parenthesis for not equal to. Similarly here X is less than B, so I'm going to shade to the left of B. It's not or equal to, this is a strict inequality, so we need a parenthesis. Here, it's also less than, so we're going to shade to the left. But this is a closed inequality, so we need a bracket, or equal to. So that's a bracket. We can make that out. Good. Now here, X is in between A and B for each four of these, but there's something different that happens with each one, at least as far as the symbols go. As far as the shading areas go, I'm just going to shade literally in between A and B for each of them. Okay, great. But now what symbols do I use? Well, when it's an open or strict inequality, we'll use a parenthesis. Where it's a closed inequality symbol, we'll use a bracket. So here it'll be parenthesis, parenthesis, bracket on A, parenthesis on B, parenthesis on A, bracket on B, and then bracket on both. Okay, good. And now, what is interval notation? So interval notation needs two numbers. It's easier for me to explain interval notation when it comes to the bottom four scenarios, because all we do is write the symbols with the numbers. The numbers here are A and B. The symbols are the parentheses and brackets. So for the last four, it's going to be parenthesis A comma B, bracket A comma B, parenthesis A comma B bracket, and then A comma B all bracket. Now you don't say it like that though. You don't say A comma B. You say from A to B, because you always go from smaller to bigger when it comes to these things. So this interval is the interval A to B, open. This is the interval A to B, closed on A but open on B. And here open on A, closed on B, and this is a closed interval A to B. So this is why we call those inequalities closed, because this is a closed inequality because there are brackets on both. This is an open inequality because it's open on both. And technically these are what are called clopen. I know it sounds stupid, but that's the actual mathematical term that people use. So yeah, you can make fun of me if you want, it's fine. But yeah, I use this in a serious tone. Right. But now what about the first four? Well, the first four, let me just say the following. We need two numbers, right? We only have one number for each of these four. So we can create a larger number in this case and a smaller number in this case. The largest number is where this ends. It's going to be what we call infinity. Similarly, the smallest number where this ends off to the left is negative infinity. Right? Good. There's a technicality. Infinity is not a number. It's figurative. It's a way to describe direction. So, since it's not a number, can you touch infinity? You can't touch infinity because it's not a number. So, what we're going to do is we're going to say that infinity will always be open. Any infinity is always open. So here's what we're going to get for the first four, actually. We get a to infinity open on both, a to infinity closed on a, negative infinity to b open on both, negative infinity to b closed on b. We see that? So we only use the parenthesis on infinity. We don't use a bracket on infinity because that implies it could be equal to infinity, and we can't be equal to infinity. It's not a number. It just describes the direction that we're moving. Right? Okay, moving on. I have these two examples here. This one's going to take a little bit of a workaround, but I'll discuss that in a second. Here, this is just how you would solve a linear equation. So I'm going to move all x's to one side, so I'll add 5x to the left. And then move all non-x's to that side, so I'll add 4 to the right. It's a little cluttered, but let's see what we get. We end up with 8x greater than or equal to 8. 4 plus 4 is 8. Divide by 8, and we get the following. We get x is greater than or equal to 8 over 8, which is 1. Now this is none of the notations we have seen here. I'm going to describe each of them in those notations. So this answer in each of these notations. So SB for set builder, that's going to be the set of all x's such that x is greater than or equal to 1. So fairly straightforward for set builder. You just write this answer that we got here after a bar, x before the bar, and all encased in these braces. Good. In graphing, well, to graph this, we only need to plot one number. The number we care about in this case is 1. So I'm going to just dash that in the middle, let's say, of the number line. And to be bigger than or equal to 1 means that we're shading the right of 1. And do we use a parenthesis or do we use a bracket? We use a bracket, yes. Why? Because it is or equal to. It's a closed inequality. So naturally we use the closed symbol, bracket. Good. Now what about interval notation? Interval notation, I'll use IN as our abbreviation for interval notation. Okay, and notice this doesn't end anywhere. It ends really at infinity, and infinity is always open. So this is going to be closed at 1, to infinity, and always open at infinity. All of these technically are the answer, but I'm going to box interval notation. It's the one we aim for. All right. So I'm going to attempt to do the next example, and I'm not going to write our answer in set builder notation nor in graphing. I'm just going to go straight to interval notation. And first off, this is what is called a three-part or three-way inequality because there are three parts of it. Instead of two halves of the inequality, there are three parts to the inequality, and naturally there are two symbols that go with that as well. So what we're going to do is we're going to do the same thing that we do to solve two-part inequalities, I guess, but whatever we do to one, we do to all three parts. So what I want to do here is I want to get rid of this 1 to get negative x by itself. So I'll subtract 1 to all three parts. Cancel in the middle, so we get negative x in the middle. The signs stay the same. This is going to be 3 minus 1 is 2. This is going to be 2 minus 1 is 1. It looks kind of funny. And in fact, you know what? I'm going to change something real quick. I'm going to make that a 4 because no number is bigger than 3 and less than 2. That was my mistake. So if it's 4, then 4 minus 1 is 3. So now negative x is in between 2 and 3. That makes a little more sense, so sorry about that. Now we are going to divide by negative 1 to get x by itself. What happens when you divide by a negative in an inequality again? Yes, the symbols reverse. So we'll get negative 2. This less than becomes greater than. Good. This is just x in the middle. This less than or equal to becomes greater than or equal to. And now we get negative 3. So I'm going to write this in interval notation super quickly. Ready? Okay, here we go. Smaller number is negative 3. Larger number is negative 2. It's closed on negative 3. It's open on negative 2. And that's it. Really, I think the hardest situation to just jump straight into interval notation is when it's not 3-part. Because 3-part, you know what the numbers are. Just write them in order and then attach the appropriate symbols with a comma in the middle, of course. When it's 2-part like this, you have to reason with which infinity to use. X being bigger than 1 means, well, infinity is the largest you can get bigger than 1, so naturally we go from 1 to infinity. And then since it's or equal to, it's closed on the non-infinity number, always open on the infinity number. So I hope that makes sense and helps. That's 1.7. So we're done with chapter 1 now, and we're going to move on to chapter 2, and I'll see you all in the next video. Thanks for watching. See you then.